Hi. So this video is to just give a short explanation about the Rapaport-Leubering shunt. So what is this Rapaport-Leubering shunt? The first question we always get when we want to read a pathway is Yavanda the kandupudicha, right? So for that particular question, the answer is here. So Rapaport-Leubering shunt was first described in 1925 by the Austrian biochemist Rapoport and his technical assistant Jane Leubering. So the person given in the picture is Rapoport, and there is no picture available in the websites for Leubering. So these two people were the scientists who discovered the Rapoport-Leubering shunt. It is otherwise known as 2,3 BPG shunt. BPG means bisphosphoglycerate shunt. So now where does this pathway occur? It occurs inside the red blood cells. So red blood cells are the major site where Rapoport-Leubering shunt occurs. So now why does it occur? எதுக்குடா இது நடந்து தொலைக்குது அப்படின்னு கேட்போம். ஓகேவா? So for that the answer is here. It is to produce 2,3 bisphosphoglycerate. Okay. So that is why it is otherwise known as 2,3 bisphosphoglycerate shunt. So how does it occur? See, the left side of the picture shows a normal glycolysis. All of you know what are the steps of a normal glycolysis. It starts from glucose and ends with pyruvate, generating around 7 ATPs in aerobic conditions up to the production of pyruvate. If it is anaerobic condition, it goes to lactate, and there it has only 2 ATPs. So there are so many ATPs which are produced in the normal glycolysis. But in case of this 2,3 BPG shunt, so this particular step where 1,3 bisphosphoglycerate becomes 3-phosphoglycerate, this particular step has been bypassed or shunted into a different step to form a different compound, which is 2,3 bisphosphoglycerate. So for this you need an enzyme 2,3 bisphosphoglycerate mutase. To convert 1,3 to 2,3 you need a mutase. From 2,3 then it goes to 3-phosphoglycerate through the enzyme phosphatase. Okay, so this is a step of synthesis of 2,3 BPG, and this is the degradation of 2,3 BPG, and that will join the glycolytic pathway, remaining glycolytic pathway. So this particular step of glycolysis is shunted to form a different compound, which is 2,3 bisphosphoglycerate. So what is the net effect of production of this 2,3 bisphosphoglycerate? Already I told you there are 7 ATPs which are produced under aerobic conditions, and there are 2 ATPs produced under anaerobic conditions. So because of this particular shunt mechanism, the net production of ATPs are nil. So we are doing something which is going to do, which is now going to avoid the production of ATPs. But still we do this inside the RBCs. Why? Because we need this compound 2,3 bisphosphoglycerate. So what is the purpose of this compound? That comes under the clinical relevance section, where what is the use of 2,3 bisphosphoglycerate. So it is one compound which is produced in our body and helps in adaptation to high altitude. So this is a clipping from Harper's textbook. So you can read this like physiological changes that accompany prolonged exposure to high altitude include increases in the number of erythrocytes. You know, there will be polycythemia when there is high altitude exposure. Along with that, there will be an increased synthesis of 2,3 bisphosphoglycerate. So elevated 2,3 bisphosphoglycerate, it will bind with hemoglobin, thereby lowering the affinity of our hemoglobin for oxygen. So hemoglobin and oxygen will not bind more effectively. Thereby, all the oxygen will be released from the hemoglobin because of the binding of 2,3 bisphosphoglycerate. So the key word here is 2,3 BPG reduces the affinity of hemoglobin for oxygen, thereby releasing the oxygen at the peripheral tissues. So in high altitude conditions, our body undergoes hypoxia. So in order to compensate for that hypoxia, we need this 2,3 BPG, which is normally physiologically produced in the body to increase the release of oxygen at the peripheral tissues. So this summarizes the 2,3 BPG shunt or Rapoport-Leubering shunt.